Hello, welcome to my channel. Today we start the series of videos concerning Green's theorem. So long story short, in this channel, I have a series on, say, mathematical problems in very basic physics, and this series of videos is some kind of like appendix to this videos because we are dealing right now with a problem of defining potential, and that's because we need to show that's why we need to show some integrals to be independent of curves, and that's why I am introducing Green's theorem. This also should explain to you why am sometimes taking detour to say something about potential, but this video is kind of self-contained. You don't need any reference to the series. You don't need to watch it like prior to watching this video. And we are going to cover. The plan is that we are going to build up whole same machinery to prove Green's theorem uh, for C1 curves. I mean piecewise C1, and that's why we will need some topological facts and such things. So that's for the starters, and now I would like you to enjoy this video. So let's start with the like technical stuff. Okay, so maybe I will refer once again to the problem that we are facing. So our problem was to define, to find integral of motions on arbitrary open sets. So the first thing that we want to do is to decompose any open set into some like simpler pieces. So that's why we need some topological facts, and that's why I am stating this theorem one. If you would look into notes, uh, it states that every open subset of the plane, it can be decomposed into simpler pieces di that are domains, and domains in the sense that these are open and connected sets. So the theorem states that any open set on the plane can be decomposed into domains, into countable family of domains, because it's not necessarily finite, but we know that it cannot have cardinality bigger than Aleph 0, and that's what we're gonna show. What's more, this fact is of course not only true for the plane, but here I am approaching it. The reason why I do all this stuff is the application in physics, and right now actually on the plane. So we are going to heavily use the fact that the plane is locally arcways connected. Because the balls are arcways connected. So this will be used in this theorem, but it is not the most general, say, theorem that we can arrive at. In general, it works for locally connected spaces. So this is something slightly weaker than local arcways connectedness, but we won't be proving it in full generality, but the proof is kind of similar. I guess so. So we prove this fact as follows. So we can define the relation that will come up to be an equivalence relation, which we will show in a second. So the relation is as follows. So we say that 2 points are equivalent if there exists a curve defined on some interval, such that the endpoints of this curve are P and Q. These points P and Q respectively. So that's how this relation looks like. And now we prove that this is equivalence relation. So reflexivity is easy because we may connect P with constant curve, so there is no problem on any interval. it is symmetric because we always might take like minus curve, in the meaning that if we choose curve from P to Q, we can always take minus the interval and minus the parametrization, and this is like reversed curve then. So there is no problem also. Uh, what's more, yeah, but remember that we still are talking about the curves uh, in the set U. So these are not arbitrarily curves in R2 because this would make no sense, but the curves in U specifically. Mhm. Okay, and the transitivity goes like this. So we can, it's just the matter of reparametrization. So we have two curves from P to Q and from Q to R. And we take, I mean, we can write down the interval, I mean, using its endpoints, and the second one also. And we just kind of glue these curves together so that the parametrization fit, and the interval is then from A1 to B1 plus B2 minus A2. So that's how the curve goes. So we basically just shift the curve, shift the parameterization so that everything is okay, and it's easy to see that the endpoints are P and R respectively. Okay, but now from the fact that we have splitting I mean that we have equivalence relation, it is, I mean, it is like basic, I don't know, basic set theory that every equivalence relation decomposes our set, our primer, I mean our prior set into disjoint pieces, and these pieces are called equivalence classes. Hmm? So that's okay. So I've written here that U splits into D, this P in brackets with tilde, and this means that we can always, I mean, write down U as the sum of equivalence classes. I mean, over equivalence classes of the sets that are these equivalence classes, we can say. Maybe it would be better written if I introduced the quotient space, I mean U over this relation, and then we sum over all, say, elements, I mean over or indices from this, say, quotient set. So maybe this would be better, but we all agree what does it mean that we can take one representant from each class and sum over these representants the sets that these representants belong into. So this is how it goes. If it of course gives us the whole U. And now we have to show some topological facts on these DPs. So first of all, this DP is open for any P, of course, for any class, I would say. Mhm. So how does it go? We know that the whole set U is open. So if we choose any point from this DP, we may choose the ball that is solely inside U. And now if we choose any P1 from the ball, we can connect it with the. Okay, so maybe just to clear things up, we want to show that this set is open, so we want to show that if we take sufficiently small radius and sufficiently small ball, then we can fit this into this DP. So we know that the points in DP are characterized by the fact that every 2 points are connectable from the curve in U. Hmm? So we choose this P1, and we need to show that we can connect it with any point from DP by the curve. So how is it shown? We just take any curve from Q to this P0 or any P to P0, and to show that P can be connected with P1, we just use the straight line segment. And this is of course still a curve, so there is no problem. And this is written in details here in my notes, but this is not that relevant. And last thing to show is that since we know that the whole curve that was like prior, I mean from P to P0, we know that this whole curve fits in U. So we need to show that this line segment fits in U also, but this is easy since the ball fits in U. So we just need to show that this segment is contained in the ball, and the calculation is here. So we have this whole subtraction here. This is the length of vector from any from P0 to any point on the segment, and we have following like natural inequalities. So first of all, I mean, first step is just subtraction. Then we estimate this t minus b by 1 because it's always less than 1. And then this p1 minus p0 is of course less than epsilon because it sits inside the ball, so there is no problem. And this shows that this line segment is solely contained in U, or even, I mean, through this ball it is contained in U. Second fact that we need, the topological fact, is that these DPs are connected, but this is easy because they are by definition arcwise connected. So there is no problem because any arcwise connected set is connected. This is fact from topology. It is always easy it is also easy to show because maybe very quick argument we can give is that if we were to split, say, if we had a splitting into two open sets, then the image of the curve, if it were to hit like both of these points, because we assume that it was arcwise connected, then it would be contradiction because we would have a splitting of the image of the curve that is a homeomorphic image of the interval, but interval is connected, so homeomorphism cannot like break this property. So okay, I mean this argument probably works only for non-self-intersecting curves because it has to be homeomorphism, uh, but this is, I mean, I am not going to make this precise because this is easy task, and I mean, the space on my paper is limited, so we need to do some things. So it is always a matter of choosing what to do and what to leave for the reader. So this is left for the reader. I mean, on our end it is even easier to show because continuity is just sequential continuity. So that's probably how I would do it. Okay, and we had one more thesis in our theorem, namely that the sum is countable. So, uh, I mean, the disjointness is clear from the fact that this is equivalence relation, but we still have to prove countability. And that's easy because from any set we can of course always, since it is open, we can always choose some kind of rational number. So we have one-to-one correspondence. I mean, not to rational numbers, but to some subset of rational numbers. So this is of cardinality at most Aleph zero. Then. So there is no problem. I mean, basically, this is like the second countability axiom or something. I mean, I just preferred to make it simpler, so I choose to do this with this argument with rational numbers. Of course, I am talking about rational numbers from the grid. I mean, q squared it is called in my notes because we are on the R2, so rationals are also on the grid. Okay, and there is also a remark that these DPs are both open and closed. So this is uh, at least for well-behaving topological spaces, uh, this is true that if we have set and we have some kind of how do we call it, some connected component, then it has to be open and closed in in this set. So it is not necessarily open and closed in Rn. It even isn't, because it has to be open in Rn, so it cannot be closed in Rn if it is not Rn. There's also the fact from topology that, I mean, probably if we have connected sets, then the only set that is both open and closed, then it has to be the whole X. I mean, the whole set under consideration. And okay, I have proof of this later, so maybe that's a bit of a look in the future. But now, why we do this? So this is again like shout out to my Polish series. So we were to define the potential, the integrals of functions over curves and such things. So now, since we decomposed our set U into simpler pieces, uh, with the with the aid of lemma that will be proved in a second, it will show that we basically may restrict ourselves into domains. Basically, we can work with domains, with connected sets, because, as I will show in a second, that if, I mean, let's take a look into my notes. So if we have this decomposition as above, then any function that is continuous or even ck class on U is, I mean, is on one hand it is, I mean, the restriction of the function onto these domains is also of class ck, and the other way around. So basically, that's why we can restrict ourselves to work into just solely into domains. So to sum up, we can work with potential like on the separate domains. I mean, the if we were to switch to different domain, this is like completely new word, and it is not connected with the previous one. So basically, we have separate problem too. If we work with some, say, differential equation, then we can work separately on the different connected components. So that's what it says. Okay, so maybe since I lost a bit of time, I mean, it took a bit too long to go through all these details on subdivision into domains of this open set. I'll just skip this proof of this lemma, because it's kind of natural. I mean, again, since we are in Rn, so in particular in R2 we have this sequential definition of continuity, and this is what I use here. I mean, this proof is I would say more or less correct. I mean, it is rigorous, but we would, for example, need to show that any sequence from x, I mean, any sequence xn in U can be, I mean, is in some way equivalent to the sequence xn tilde in di. But this is very easy problem, so I will again I will leave it to you. So please maybe pause the video and go through this proof. And if you had, for example, any questions, I invite you to comment the video, and I will respond, obviously. Okay, so now we are struggling with a bit different problem, because now we have to deal with the integration, because now we have curves, we have like arcwise connected sets, so we know that any point can be reached with a sound curve, but now we need to choose some class so that we are able to integrate over it. So the class that is most common used to define integral over a curve is the so-called class of bounded variation curves. So this is how it's done in most textbooks and such. But we don't need to work with that much of, say, I mean, with that weak class. So I choose to choose the class of piecewise Celan functions, and it will be shown in a moment that this class mm, is sufficiently restrictive to, sufficiently not restrictive to still connect any 2 points in our connected component. So this will be shown in a moment, and this is important for us because we have to be able to construct this potential. So we have to be able to connect any 2 points. So that's the reason why I am using this class. And okay, so about these bounded variation curves, we know that these are like differential almost everywhere in Lebesgue measure. This is what is written here, and this is like deduced from Rademacher's theorem. So if anyone is interested, please go and check it because it's very deep analytical theorem. Okay, and about the definition of the integral is, the idea is to define it in such way as is written in my notes. So the integral of the function f over the curve gamma is the integral over the interval of f of gamma times the derivative of gamma. And this is very natural definition because it in some way take like the increment of the curve gamma. This small increment, and integrate f over those increments. So this is how we imagine that integral look like. This is, in most say textbooks, this is the way to define the Riemann-Stieltjes integral over, say, using the function gamma. And we know that this integral is defined for the functions of bounded variation. So that's exactly what we need here. So if anyone is interested in this, so this is called Riemann-Stieltjes integral, as I said. So if you want, maybe Google it or something. You can find plenty information on that. So I recommend you to do so. Then, of course, since C1, piecewise C1 class is very much more restrictive than this. We know that these C1 functions are in particular of bounded variation. So we can integrate over those curves. And now what we are to show is that any connected set on the plane is not only path connected, but it is piecewise C1 path connected, so that we can connect any two curves by C1 curve. And that's proven used the lemma that I introduced here. So say X is a connected set, then U, if is both in topology and in cotopology, then U have to be whole X. So if U is both open and closed, then U has to be equal to X. So this is the lemma that I mentioned when we were after this decomposition of any open set. Mhm. Okay, so proof is very easy. So proof is by contradiction. So assume that U is not equal to X. Then we have this decomposition into U and X minus U. But X minus U has to be open since U is closed. So X minus closed set is open. And these two intersect, of course, in no point because these are disjoint like, I would say by definition or by very quick argument. But now we have decomposition into two open sets that are disjoint and which give the whole X. So this is basically what the connectivity is not. So we proved that if this is the case, then X cannot be connected, but we assume it was connected. So we have a contradiction. Okay, so I guess I will stop here, and in the next video we will finish this topological considerations. I will prove that what's written here, that any connected and open set in the plane, so any domain, is C1 path connected piecewise. So that's what we need to be able to establish some reasonable potential on connected sets. And we'll probably head like finally to the Green's theorem. So that's what we need. And probably the proof of Green's theorem will be subdivided into 2 videos. So stay tuned and see you in a bit.